Hydrocolloids or gums are a diverse group of long-chain polymers characterized by their property of forming viscous dispersion and or gels when dispersed in water. These materials were first found in exudates from trees or bushes, extracts from plants and seaweeds, floats from seeds or grains, gummy slimes from fermentation processes, and many other natural products. Occurrence of a large number of hydroxyl groups noticeably increases their affinity for binding water molecules, rendering them hydrophilic compounds. Further, they produce a dispersion which is intermediate between a true solution and a suspension and exhibits the properties of a colloid. Considering these two properties, they are appropriately termed as hydrophilic colloids or hydrocolloids.
Hydrocolloids have a wide array of functional properties in foods, including thickening, gelling, emulsifying, stabilization, coating, etc. Hydrocolloids have a profound impact on food properties when used at levels ranging from a few parts per million for carrageenan in heat-treated dairy products to high levels of acacia gum, starch or gelatin in jelly confectionery. The primary reason behind the ample use of hydrocolloids in foods is their ability to modify the rheology of food systems. This includes two basic properties of food systems, that is, flow behavior, viscosity, and mechanical solid property, texture. The modification of texture and or viscosity of food systems helps modify its sensory properties. Therefore, hydrocolloids are used as significant food additives to perform specific purposes. It is evident that several hydrocolloids belong to the category of permitted food additive in many countries throughout the world. Various food formulations such as soups, gravies, salad dressings, sauces and toppings use hydrocolloids as additives to achieve the preferred viscosity and mouthfeel. They are also used in many food products like ice creams, jams, jellies, gelled desserts, cakes and candies to create the desired texture.
Pectins and gums are important polysaccharides in foods because of their functional properties. They are widely used as gelling agents, thickeners, and stabilizers. They are constituents of plant tissues and are large complex molecules whose exact nature is not certain. However, enough is known to understand some of their properties and to make use of their functional properties to produce convenience and special texture foods.
Pectic substances, including protopectin, pectinic acid, and pectic acid, are an important constituent of plant tissue and are found mainly in the primary cell wall. They also occur between cell walls where they act as intercellular cement. Although their exact nature is not clear, they can be considered as linear polymers of D-galactonic acid joined by alpha-1 4 glycosidic linkages. Some of the acid or carboxyl COOH groups along the chain are esterified with methanol CH3OH as shown. Each glycosidic linkage is a cross-planar bond because it is formed by reaction of one hydroxyl group located above the plane of the first ring with another hydroxyl group located below the plane of the second ring. The configuration of these bonds causes twisting of the molecule and the resulting polymer can be likened to a twisted ribbon. Cross-planar bonds are not readily digested in the human digestive tract, and so pectins are classified as soluble fiber.
Pectic substances may be grouped into one of the three categories depending on the number of methyl ester groups attached to the polymer. Protopectin is found in immature fruits and is a higher molecular weight methylated galacturonic acid polymer. It is insoluble in water but can be converted to water dispersible pectin by heating in boiling water. It cannot form gels. Pectinic acid is a methylated form of galacturonic acid that is formed by enzymatic hydrolysis of protopectin as a fruit ripens. High molecular weight pectinic acid are known as pectins. Pectinic acids are dispersible in water and can form gels. Pectic acid is a shorter chain derivative of pectinic acid that is formed as a fruit over ripens. Enzymes such as polygalacturonase and pectin esterase cause depolymerization and demethylation of the pectinic acid respectively. Complete demethylation yields pectic acid, which is incapable of gel formation.
Pectins. Pectins are high molecular weight pectinic acids and are dispersible in water. Some of the carboxyl groups along the galacturonic acid chain are esterified with methanol. The degree of esterification in unmodified pectins ranges from about 60% in apple pulp to about 10% in strawberries. Pectins can be deliberately deesterified during extraction of processing. According to the degree of esterification, pectins are classified as high methoxyl or low methoxyl pectins. The two groups have different properties and gel under different conditions. Low methoxyl pectins. Low methoxyl pectins contain mostly free carboxyl groups. In fact, only 20 to 40% of the carboxyl groups are esterified.
If sufficient cross-links are formed, a three-dimensional network can be obtained that traps liquid, forming a gel. Low methoxyl pectins thus can form gels in the presence of divalent ions without the need for sugar or acid. High methoxyl pectins. High methoxyl pectins contain a high proportion, usually 50 to 58% of esterified carboxyl groups. Most of the acid groups, therefore molecules for each other, must be increased. This can be achieved by addition of sugar and acid. Sugar competes for water, thus making less water available to associate with the pectin molecules. This reduces the attractive forces between the pectin and water molecules. Acid adds hydrogen ion, reducing the pH. The pH must be below 3.5 for a gel to form. Carboxylic acids contain a carboxyl group COOH are weak acids and are not fully ionized in solution. The unionized form of the acid exists in equilibrium with the ionized form.
When hydrogen ions are added, they react with some of the ionized carboxyl groups to form undissociated acid groups. In other words, the equilibrium is shifted to the left and more of the carboxylic acid is present in the unionized form. Thus, when hydrogen ions are added to pectin, the ionization of the acid groups is depressed and the charge on the pectin molecules is reduced. As a result, the pectin molecules no longer repel each other. In fact, there is an attractive force between the molecules and they align and interact at specific regions along each polymer chain to form a three-dimensional network. These regions of interaction are called junction zones, shown diagrammatically in figure 7.3. However, there also are regions of the pectin chains that are not involved in junction zones because they are unable to interact with each other. These regions form pockets or space between the junction zones that are able to entrap water. Hence, a gel is formed with water trapped in the pockets of the three-dimensional pectin network. Exactly how the junction zones form is not certain, but hydrogen bonds are thought to play an important role. The steric fit of the molecules, in other words, their ability to fit together in space, also is important. Pectin molecules contain minor components such as rhamnose and other neutral sugars that are bound to the main galacturonic acid chain by 1,2 glycosidic links. These sugars cause branches or kinks in the molecules and make it difficult for them to align and interact to form junction zones. However, there are regions of the pectin chains that do not contain these neutral sugars, and it is these regions that are thought to form the junction zones. High methoxyl pectins form gels in this way. Low methoxyl pectins require divalent ions to gel, and intermediate pectins require sugar, acid and divalent ions to gel.
Pectin sources. Pectins with a high molecular weight and a high proportion of methyl ester groups have the best jelly forming ability. The pectin content of fruits is variable and depends not only the type of the fruit but also on its maturity or ripeness. Purified pectin is made from apple cores and skins, apple pomace, and from the white inner skin, albedo, of citrus fruits. It is available in either liquid or granular form. The granular products have a longer shelf life than the liquids. Low methoxyl pectin can be obtained by demethylating pectin with enzymes, acid or alkali until it is 20 to 40% esterified. Because these pectins gel with divalent ions and need no sugar, they can be used commercially for the production of low-calorie jams, jellies or desserts. They also have been introduced to the retail market so that such low-calorie products may be made at home.
Gums. Gums are a group of complex hydrophilic carbohydrates containing thousands of monosaccharide units. Galactose is the most common monosaccharide found in gums. Glucose is usually absent. Gums are often referred to as hydrocolloids because of their affinity for water and their size. When added to water, they form stable aqueous colloidal dispersions or salts. The molecules are highly branched, and as a result, most gums are unable to form gels. However, they are able to trap or bind large amounts of water within their branches. Aqueous dispersions, therefore, tend to be very viscous because it is difficult for the molecules to move around freely without becoming entangled with each other.
Gums are classified as soluble fiber because they undergo little digestion and absorption in the body. Therefore, they supply relatively few calories to the diet as compared with digestible carbohydrates such as starch. Gums are common in a wide range of food products including salad, dressings, sauces, soups, yogurt, canned evaporated milk, ice cream and other dairy products, baked goods, meat products and fried foods. They are used as thickening agents in food products, replacing starch. They also are used to assist in the stabilization of the emulsion and to maintain the smooth texture of ice cream and other frozen desserts. They are common in reduced fat products because they are able to increase viscosity and help to replace the texture and mouthfeel that was contributed by the fat. Gums are obtained from plants and can be separated into 5 categories: seed gums, plant exudates, microbial exudates, seaweed extracts, and synthetic gums derived from cellulose.
The seed gums include guar and locust bean gums. These gums are branched polymers containing only mannose and galactose. Guar gum contains a mannose-galactose ratio of 2:1, whereas the ratio is 4:1 in locust bean gum. Guar gum is soluble in cold water, whereas locust bean gum must be dispersed in hot water. Neither gum forms a gel when used alone. However, they may be used synergistically with other gums to form gels. Guar gum forms gels with carrageenan and guar gum. It is used to stabilize ice cream and it also is found in sauces, soups and salad dressings. The presence of guar gum in the intestine seems to retard the digestion and absorption of carbohydrates and slow absorption of glucose into the bloodstream. Use of guar gum in foods, therefore, may be useful in treating mild cases of diabetes. Locust bean gum typically is used as a stabilizer in dairy and processed meat products. It also may be used synergistically with xanthan gum to form gels.
The plant exudates include gum arabic, which comes from the acacia tree, and gum tragacanth. These are complex, highly branched polysaccharides. Gum arabic is highly soluble in cold water and is used to stabilize emulsions and to control crystal size in ices and glazes. Gum tragacanth forms very viscous solution and is used to impart a creamy texture to food products. It also is used to suspend particles and acts as a stabilizer in products such as salad dressing, ice cream and confections.
Xanthan gum, gellan gum, dextran and curdlan are all gums produced using fermentation by microorganisms. Of these, xanthan is the most common. Xanthan forms viscous solutions that are stable over a wide range of pH and temperature. It does not form a gel except when used in combination with locust bean gum. It is used in a wide range of products as a thickener and stabilizer and suspending agent. Most salad dressings contain xanthan gum.
The seaweed polysaccharides include the agars, alginates, and carrageenans. Unlike most other gums, they are able to form gels under certain conditions. Carrageenan is obtained from red seaweeds, especially from Irish moss. It occurs as three main fractions known as kappa, iota, and lambda. Carrageenan. Each is galactose polymer containing varying amounts of negatively charged sulfate esters. Kappa carrageenan contains the smallest number of sulfate ester and therefore it is the least negatively charged. It is able to form strong gels with potassium ions. Lambda carrageenan contains the largest number of sulfate groups and is too highly charged to form a gel. Lota carrageenan forms gel with calcium ions. The carrageenan fractions generally are used in combinations. Several different formulations are available containing different amounts of individual fractions, and food processors are able to choose formulations that best fit their needs. The carrageenans are used to stabilize milk products such as ice cream, processed cheese, canned evaporated milk, and chocolate milk because of their ability to interact with proteins. The carrageenans also may be used with other gums because of their ability to cross-link with them. Agar also is obtained from red seaweeds. It is noted for its strong, transparent, heat-reversible gels, that is, agar gels melt on heating and reform when cooled again. Agar contains two fractions, agarose and agaropectin, both of which are polymers of beta D and alpha L galactose. Agaropectin also contains sulfate esters. The alginates are obtained from brown seaweeds. They contain mainly D-mannuronic acid and L-guluronic acid, and they form gels in the presence of calcium ions. Calcium alginate gels do not melt below the boiling point of water. Thus, they can be used to make specialized food products. Fruit purees can be mixed with sodium alginate and then treated with calcium containing solution to make reconstituted fruit. For example, if large drop of cherry alginate puree are added to calcium solution, convincing synthetic cherries are formed. Reconstituted apple and apricot pieces for pie fillings also can be made by rapidly mixing the sodium alginate fruit puree with a calcium solution and molding the gel into suitable shapes.
Synthetic gums. Cellulose is an essential component of all plant cell walls. It is insoluble in water and cannot be digested by man, so it is not a source of energy for the body. It is classified as insoluble fiber. The polymer contains at least 3000 glucose molecules joined by beta-1 4 glycosidic linkages. Long cellulose chains may be held together in bundles forming fibers as in the stringy parts of celery. Synthetic derivatives of cellulose are used in foods as non-metabolizable bulking agents, binders and thickeners. Microcrystalline cellulose, known commercially as Avicel FMC Corporation, is used as a bulking agent in low-calorie foods. It is produced by hydrolysis of cellulose with acid. Carboxymethyl cellulose (CMC) and methyl cellulose (MC) are alkali modified forms of cellulose. The former is the most common and is often called simply cellulose gum. It functions mainly to increase the viscosity of foods. It is used as a binder and thickener in pie fillings and puddings. It also retards ice crystal growth in ice cream and the growth of sugar crystals in confections and syrups. In dietetic foods, it can be used to provide the bulk, body and mouth fill that normally would be supplied by sucrose. Methyl cellulose forms gels when cold dispersions are heated. It is used to coat foods prior to deep fat frying in order to limit absorption of fat. Two other forms of modified cellulose include hydroxypropyl cellulose and hydroxypropyl methyl cellulose. These also are used as batters for coating fried foods.
Functional roles of gums. Gums may be used to perform one or more of the roles in food products. Thickeners, salad dressing, sauces, soups, beverages. Stabilizers, ice creams, icing, emulsified products. Control crystal size, candies. Suspending agents, salad dressings. Gelling agents, fruit pieces, cheese analogues. Coating agents, batters for deep fried foods. Fat replacers, low fat salad dressings, ice creams, desserts. Starch replacers, baked goods, soups, sauces. Bulking agents, low fat foods. Source of fibers, beverages, soups, baked goods.